Welcome to Resolver. In this demonstration, we're going to show you how to export an existing project from a simulation tool like Visual Components, optimize the path using Resolver, and then import it back into your simulation tool. Displayed here is a demo study of spot welding applications. Robots R1 and R2 have sequences labeled before. It's important to note that neither R1 nor R2 are sending set or wait signals, nor are their interfaces connected. The sequences include spot weld points and home locations. Let's run our program in the main sequence, calling the before sequence in the main statement and playing it. You'll notice that when the robots are moving, each one collides with the workpiece due to the absence of registered via points. Essentially, the robots know their destinations, but they don't know the path to get there without colliding. Adding to this, the robots start moving independently, leading to a collision in the middle. This happens because they aren't communicating with each other. Resolver is designed to solve these types of issues and provide you with the shortest cycle time path. To start, you'll need to export your project using the Realtime Robotics connector. After installing the connector, make sure this icon is checked so it's visible on your screen. When you first install, you might need to sign into the connector using your Resolver account credentials. If you do not have account, you can request one at rtr.ai/demo. I'll start entering my credentials and then go to the Export tab. As you can see, we have an Export tab, a Resolver tab, and an Import tab. When you're signing into Resolver, make sure your cloud environment is set correctly. In my case, it's set to Global. The next step is to select the sequences you want to export and optimize on Resolver. In this case, I have selected a before sequence for each robot. Click on Export to export these sequences to the Resolver. A pop-up warning message will appear, asking to define the self-collision rules. We strongly recommend enabling and correctly defining these rules, but for this demonstration, I will proceed without it. Depending on the project size, the export process might take some time. Once the export is successful, a success message will appear on the output panel. We can then return to the Resolver page. As you can see, we have transitioned to a different interface that displays the sequences we uploaded for optimization. We can see here Robot R1 and Robot R2 with their respective sequences. To begin optimizing the sequence for the first robot, we need to configure the Resolver settings. Start by setting the target offsets for the approach in the X, Y, and Z directions. You can also specify the degree at which the tool needs to approach the workspace. The same can be done for the depart offsets. In each tab, you can enter positive and negative values. For instance, if you want the tool to move in the opposite direction of the Z-axis, you can enter a negative value, such as -50 millimeters. Next, let's discuss allocation. In the allocation settings, you can specify if one robot can perform the tasks of another. For instance, in this spot weld application demo, it doesn't matter which robot performs a spot weld at a particular point. Our priority is to reduce the cycle time. To achieve this, we utilize the optimized target order functionality. This feature allows us to shuffle the order of spot weld points. For instance, in our case, the first point for Robot 1 after the home position is P2. This is followed by P3 and then P4. Now, if the Resolver determines that the cycle time would be shorter, by going to point 3 before point 2, it will create a new path, home to 0P3, then to point 2, and so on. As this is a spot welding application, the order of tasks is irrelevant, which is why we can shuffle the points. When this button is toggled on, the Resolver automatically locks the home positions and optimizes only the target spots. Next, we have interpolation. We can decide if the interpolation is joint or linear for all points, or specify a specific target for motion. In linear motion, the resolver attempts to find the path using linear interpolation. If it cannot, it automatically switches to joint interpolation to provide the path. Finally, we have configuration settings. These settings allow you to maintain your joint configuration. If you're handling material, you might want to keep this configuration as the pick and place rotation matters. Alternatively, you can optimize the configuration where the resolver tries to optimize each joint value's configuration or specify the axis you want the path to be optimized on. For instance, in a spot welding application, the end rotation of the tool in the Z-axis isn't crucial. Thus, we can choose to optimize the tool RZ. We can also specify the task duration. Let's assume each spot weld takes 1 second. Next, we'll apply the same settings for other robots before the sequence. We'll save these settings, optimize, and set the task duration to 1 second each. In the View Query settings, we have the option to enable smoothing. We'll leave this toggle button on. Since this is the end condition, we can define when our resolver starts and stops optimizing. Now, we'll click the Start button. The interface will change once again. Depending on the project size, these steps might take some time. What's happening now is that the resolver is creating an application-specific server and connecting it to the cloud. It will then load up the project and check for any project errors. Once those steps are completed, the optimization process will begin. Once the optimization starts, you will be shown the reachability table. This table shows that all robots combined have a total of 12 waypoints, with 6 being reachable and 6 not. If you recall, we tried to assign Robot 2's targets to Robot 1 if they were reachable and vice versa. That's what we can see here. For each robot in our sequence, we registered 3 waypoints or task points. We then tried to assign the targets of the other robots to the opposite one, if it could reduce the cycle time. However, as we can observe, the registered waypoints for Robot 2 are not accessible by Robot 1, and similarly, the waypoints of Robot 1 are not accessible by Robot 2. This is why they are marked in red. However, the original registered points for both Robot 1 and Robot 2 are now accessible without any collisions. You can download this data for future use as well. Next, we observe that after some time, the estimated cycle time is displayed. As soon as the optimization begins, within a few minutes, it provides a collision-free, shortened cycle time result. After a while, it will automatically stop optimizing, depending on your condition settings. Here, you can also see the result preview of the robot movement. As observed, the robots are not colliding. Once you are satisfied with the result, you can click on Download Results. This will display a pop-up with a choice of interlocks, offering sequence or spatial interlocks. In this case, we have been provided with 2 spatial interlocks and 1 sequential interlock. The difference between spatial interlocks can be seen in the interlock count. From this, it's clear that a higher number of interlocks results in less cycle time. For this case, we will proceed with the sequence interlocks import. Now, as you can see, the resolver result was successfully imported. On the left side, we have the RTR opti sequence automatically added for each robot. This is the before statement and the RTR opti statement. As you can observe, we've added via points to the original program and inserted sync statements, which facilitate signal transmission from one robot to another. Let's replay the previous sequence statement. As noticeable, the robots and tools are colliding, and the tool is also colliding with the workpiece. Now, let's transition the statement from the previous one to the newly optimized RTR opti for each robot. Let's replay this sequence. As evident now, there is no more collision. Thanks for watching. To learn more about using Resolver, visit resolver.rtr.ai.